Okay, so welcome back. So this is the last video. This will be the last module in as far as the theory goes, as far as the 4-week course content goes. We'll have another a tutorial video which will go over some of the problems. So that will be really helpful for those of you who are planning to take the exam. It will be helpful for everyone, and of course, it will help the people who are who are registered for registered or planning to register for the exam. I'm not sure whether the date is over or not. You can check that on NPTEL website. So we'll continue our discussion that we were having this week regarding having a concept of systems thinking, the concept of life cycle analysis, trying to design a better electronic product, and that's true for any product, but our focus here is on electronics since we are talking about electronic waste. So today we'll take the discussion a bit forward and look at some of this economic balance hybrid life cycle assessment of a laptop computer. So if you have a laptop computer, how to go about economic analysis as well as looking at the life cycle analysis. See, sometimes things may be cheaper when you look at it, but if you look at the life cycle costing of that, it may come out to be much costlier. So we'll discuss those aspects in this particular module, and then this will be the kind of end of this course. So in this we'll very quickly we'll have a introduction, methodology, what is economic balance hybrid model. We put a contest for the laptop study. We'll talk about manufacturing versus use, laptop versus desktop, those comparative will be done. And so in terms of the study background, energy usage, as we were talking about from the very beginning, the use of energy over the life cycle of personal computers. So those of you who are who will be involved in designing of any electronic product, here we are talking about personal computer, desktop or laptop, but any electronic product, if we can make it more energy efficient, anything which uses energy, any product which uses energy, if we can make it more energy efficient, we are actually doing good for the environment. We are not only saving the energy bill, of course we do, we are reducing the electricity bill, of course that helps the purse, but at the same time we are also helping the environment, because that means less energy will be required. If you are working with coal based thermal power plant, that means less coal will be burned, less coal will be mined, and all the environmental footprint associated with that will get reduced. So energy use will use as an important consideration over the life cycle. And then we also will talk about this OEM. Now what is OEM? Operation and maintenance cost. So in operation and maintenance, increasing attention by consumers and OEMs in terms of the also life cycle energy impact and carbon footprint. So all those things we'll talk about. So similar, like if you if you talk about the smartphone, one problem we see with many of these smartphones is after a certain time the battery starts discharging very quickly. So earlier when like when you buy, I'm just taking my example, when I bought a phone like almost a year ago, at that time it was I will charge in the morning and then probably it will be good until late evening it will work. But nowadays if I have 100% in the morning, by afternoon I see the phone is discharging, and that I hear from many people, because either it may be because we are using too many applications, too many apps, or we are not using it properly, maybe we are not charging it. There are different theories out there. You are supposed to let the mobile discharge to almost 0%, then only you should recharge it. I'm not sure whether that's true or not, but people say that, some people have told me that, and there are others say that you should not let it go down below 25%, because below 25% actually it starts draining the battery very fast, and then it's not good for the health of the battery, health of the cell phone. You should charge it when it's below 25%. I'm not sure which one is the correct one. If some of you who are electrical or who knows about battery much more than probably educate us through the discussion board, we'll be more than happy, because that's a big problem. If you're trying to recharge your phone every day, twice or 3 times a day, especially when it gets a little bit older. When it's new, it works fine, even with all those applications. When it gets older, it doesn't work properly. And the other theory is that if you use this power bank, that also destroys your battery. I'm not sure, but those are the things which I have heard from different people. But how much is the surety? I don't know. At least let me know if you know that. It will be nice things to know. So the operation and maintenance, that's of course is there. And the goal is basically to do the evaluate to inform what are the design changes required to make the electronics, make this laptop more environmental friendly, and also the behavior and use changes which we will talk about in a minute. So, life cycle assessment, you already know that. We will just skip this slide, just take another sketch for the same thing that we have been looked at earlier. You are doing a quantitative method. So, essentially you have a quantitative method. To estimate system level impacts of a product or service over its entire life. So, you are having a trying to have a quantification of the method to find out to estimate the system level impact. So, that is what we do in LCA. You have seen several examples already, and at the bottom you see those material extraction, processing, manufacturing, use, and waste management. So, here there are two approaches: bottom up process sum LCA, where there will be certain uncertainty with a cutoff error. Then also there is a top down environmental impact with LCA, which is uncertainty associated with aggregation. So, there are two approaches are there. So, it says let us go for something like an economic balance hybrid LCA, which is kind of reduces the overall uncertainty. So, it's you take the top down approach, the bottom up approach, and then try to mix it together and come up with the economic balance hybrid LCA, and try to reducing the uncertainty, essentially the uncertainty of the data, because the data, as you know from LCA exercise, lots and lots of data go there, and if the data quality is not correct, if there is a lot of uncertainty in the data, of course that reflects in your LCA result. So, that is what we need to look at. So, we will try to look at what is this economic hybrid LCA, which is trying to reducing. So, contest for hybrid methodology, previous study they have done applying LCA to desktop computers. They underestimate, the study has been shown that it underestimate manufacturing impact by process LCA alone. If you look at the process LCA, it underestimates the impact. So, then as you can see over here, Williams, there are several studies listed over here, and the type of LCA was done, whether it is a process based, hybrid, or manufacturing. As you look at the impact, the hybrid shows more impact in terms of the manufacturing, while the others in the process based, different methodology was used. You see the ranges from 20 to 80%, but this one showed 80%. So, we do not really to evaluate this further, we will like to look at how this hybrid methodology is used. So, we do a case study, which if you take the Dell Inspiron 2500, which is Intel Pentium 3 processor, this much of memory, this much of LCD screen, not a brand new computer, it looks much older, maybe around 10 years older model. Then its cost is around around 10 years ago, it is around 1450 in 2009 in US dollar. That was the cost, mostly used for residential purposes. So, this is your then you disassemble it, you find out bill of materials. So, that is really the important part of any electronics, is you need to know what are the components which goes into making it when you are trying to do an LCA exercise. So, if you have an older laptop, you can just disassemble that. We have a paper in Science of Total Environment where we have compared two ways of hand drying. So, if you go to airport these days, many airports have that what should I say, like a hand dryer which works with hot air. So, you can put your hand in there, and then your hand will get dried, or sometimes it is at the bottom as well. There is a blower, hot air blows on you, and then the hand gets dry. Other option is you take out those paper towel and then wipe your paper towel and you throw it away. So, there are both options we compared in terms of what is its life cycle analysis for using either of those two options, and the paper is already out there. Those of you who are interested, you can find that through my Google Scholar profile, or if we can put a link on discussion forum as well. If you need to, just let us know. But there we had the reason I am left into the study is we wanted to know what is there in those hand dispenser and what is there in those hand dryer. So, we took an old version of it and took it apart. We took it apart and looked at all the different components. We weighed the component. For some of the components which we could not sure, we contacted some of the material scientist people. We even did some XRD and XRF to find out what is in there. So, you need to do those kind of stuff. That is what I am trying to say. So, here as well, in terms of laptop, it was disassembled. Then they tried to look at all the material which is there. So, they had to look at the bill of materials, bill of components. So, they looked at all the materials which is present, and after they had a process some energy, like find out what is the how much energy is required. They did the economic data calculation. Then you lose the EIU LCA model in case of how much energy is required. Then after a certain year, what is the remaining value? What is the remaining value energy in that particular computer? Then we found out the manufacturing energy. That means what goes into making this particular computer, how much energy is required. Then that's the manufacturing part. And now we need to look at the use phase data as well. We need to find out how much during the usage, what happens to it. So during the use phase data, we use the use phase energy out of this how much what is the how much time how quickly you need to charge the battery, and how long lasts, how many hours you can use that battery for, what kind of battery it has, power requirement, and all those things that will give you use phase energy. So based on the manufacturing energy and the use phase energy, you will get the total life cycle energy. So if you look at from the energy point of view, you need to look at both. It's not only the use phase energy. The use phase energy is important, as well as the manufacturing energy when you are looking at the life cycle of a laptop, because if laptop is there which requires very frequently charging, then there is you will end up using lot of energy to charge it, although it may be made of material which is environmental friendly. But at the same time, if you have a laptop which once you charge, it also depends on the type of battery you have, and it lasts for a longer period of time because the processors are much better, more energy efficient, and that makes it usage much simpler to use that. So it's much better in terms of the environmental footprint in terms of the use phase energy. So we need to look at the both aspects, manufacturing energy as well as the use phase energy, to compare. So we can do energy intensity calculation based on the fossil fuel input for EcoInvent and other databases. We talked about the EcoInvent database. So we can, if it's a fossil fuel or it's a non-renewable energy, minimum maximum range to get the geographic and manufacturing variability, because geographically some places you may have more coal, less some other place you may have more hydro. So you can look at the minimum and maximum range in terms of the energy. Also the manufacturing variability will be there in the supply chain, depends on where things got manufactured, what kind of energy they used. So if you use and then in the use phase, if you have like a lifespan of almost around 3 years, and if you look at how much off mode, sleep mode, idle mode, so how will you get these data? You try to do some survey, talk to some people, and try to find out what is the typical usage they have. So we have to do some data collection into the people's behavior, people's usage behavior, and how much is off sleep or idle, and then what is the power requirement. Even in the offs, you have certain power requirement. Then sleep, you have some, and the idle also it has certain power based on how much time it is off or sleep or an idle. There are certain power requirement which goes there. So the power value for the use models, and here it may include the it's for the usage. It's a use phase. Yeah, it is for the use phase assumption. So this is the data for the use phase, not for the manufacturing phase. Bill of materials, if you look at different types of plastics, printed circuit boards, other plastics, glass, copper, aluminum, steel, and others, that's the research mass in grams. So you have this student is taking it apart and sees weighing the different components from this laptop and finding these material. This may not be the total exhaustive list. There will be some more material there, like a gold, silver, epoxy, palladium, nickel, zinc, neodymium, tin, lead. So here, as you can see, one laptop, and this is again, I'm saying this is not the complete list. There are a lot of other material out there, but if you look at even these ones, there's say 1, 2, 3, 4, 5, 6, 7, 8, and 10, like 8 and 8, 16. At least 16 material and more being used in just in a laptop, and so all these has certain environmental footprint. Then material energy, in terms of the energy consumption, how much the energy they require, low in terms of to produce that, how much energy is required to make glass or copper or aluminum. So megajoule per computer. So this is your low and high, and this is we are talking about manufacturing phase, not the use phase. Don't get confused. This is the material energy required to produce this material, which will go into the laptop. So that's what we are looking at here. So and for the other materials here as well. So this is what is the energy, and that's why you are low and high depending on where you are, depending on the efficiency of the process, where it is being manufactured. There are different countries based on the technology. that is being used to make those stuff in terms of the gold or silver and other stuff, whether it is being produced in country X versus country Y using process A or process B, the values do differ. Then you take the data and you try to do a process sum energy. So, like how much is the total energy that is required in terms of like a semiconductor, circuit board, silicon wafer, LCD and the computer assembly. If you look at the total energy and the fossil fuel also is given, and electricity, how much kilowatt hour normalized. So, you have total energy like megajoule per computer, and for semiconductors it is 274. This is again range 30 to 43, silicon wafers, LCD, computer assembly. So, these are we get the process sum energy, the energy that is used to make this particular product. Then you look at your additive input output in terms of value per laptop, how much is the value in terms of the laptop, total intensity like megajoule per dollar. We had the megajoule initially, now megajoule per dollar. Then you can find out what is the total energy per laptop, and you get in terms of the megajoule how much energy that goes in there. So, this is how you find out from the energy input. You can find out what is the CO2 equivalent, what is the minimum and maximum value in terms of the CO2 equivalent that is coming out. So, in terms of the manufacturing phase, use phase and the life cycle total phase, what is the carbon dioxide equivalent, because every impact is finally converted to a CO2 equivalent. Then you look at in terms of the material manufacturing and with this EIO corrections, where they are trying to get rid of some of the uncertainties, and this is your use phase. So, laptop low, laptop like a high because based on range. Then you have the European some project report, then desktop. As you can see, the total is 100%, but where the majority input is contribution of total life cycle energy. So, in terms of the material used, you see that at the bottom. Manufacturing is kind of in the middle, and it tells you based on the different manufacturing methods. You have different values out there for high high duty laptop, heavy duty laptop to the lower variety of laptop. What EIO correction, what is just to get rid of the uncertainties in there. And the use phase, as you can see, depending on where you are in the world, based on the type of energy that you use, you will have a lot of the use phase is still is one of the kind of the predominant phase, where based on the energy requirement during the usage in terms of the life cycle energy required. So, as the lifespan lower manufacturing and the higher manufacturing, your contribution of the use phase. For the lower manufacturing, as you can see, the use phase kind of keeps on going when it gets older. So, after say 6 years or so, you almost 60% of the footprint is coming from the use phase rather than the material production phase. And for better manufacturing, you kind of goes down to around 50%. So, that's kind of gives you the value between a better computer than a not so good computer in terms of the environmental footprint. That you can even see that many times as your laptop gets older, it gets more and more heated up. You see things getting heated up. So, it is using lots of energy is getting dissipated. Energy is getting converted into heat energy, and that energy is getting away. So, we are losing that heat as well. So, that is it become the energy usage actually goes up when you have all these heating and other things happening with that. So, total energy burden of laptop computer is significantly less than of a desktop. We saw that manufacturing component is around 60 to 70%. Depending on how you make the assumptions. EIO corrections are 40 to 50%. You should apply that in terms of supply chain input and other stuff. So, that is like in terms of how this kind of methodology is used to find out kind of life cycle impact, especially from the energy point of view for a computer. So, that is one example. When you try to design something, you can do these kind of calculations to find out which one when we go for a better design, what is the real impact in terms of the energy usage and energy saving in terms when we go for better laptop design or a desktop design. We will talk about very quickly, like if you have an institutional management of used computing equipment, how it is done. So, in terms of here, we will have some introduction, motivation, some institutional case study, benchmarking survey, some examples here, implications for research and policy. Let us do it really quickly. So, when you if you are running an institution, or if you are in a college or a university, you produce a lot of electronic waste. The question is what to do with all this stuff. So, approach is look at the sustainability trade-off associated with end-of-life management option, then benchmarking survey, how broader implications. So, we will look at a case study at a large university, and we will talk about documented surplus property via public auction for 6 months. So, there is a purchasing entity, age, brand and type, the sell price. So, what we try to do is essentially a particular institution, what they try to do is they will put a tender out where they will say that okay, we want to get rid of all these old computers which we have. And when we say computers, it is not only computers, printers, scanners, Xerox machines, so all those old electronics that they want to get rid of. And then there is a sell price range, like how much there is an expected value, and then based on how people will bid, based on that you have an estimate of the price, and then you based on the bidding price that people come forward with, you decide how much it will cost you, like how much you will charge based on the, and then based on the bidding, whoever bids for the higher value, you give the material to them. One thing, as per the e-waste management rules, we have to make sure that it goes to a registered recycler now. It has to be a registered collector, registered recycler who is registered with the State Pollution Control Board and Central Pollution Control Board. So, it has to go there as an institution. So, this is just one example where they looked at units sold in 2008, average age, and in the bracket you see standard deviation. Age range, some got bad even at 1.4 like years, and some were even for 23 years people used it. Then average price in terms of how much is the price value left, and then what is the estimated value left, and then sale price ranges in which it got sold. So, depending on which people have what value people have seen it. So, in terms of the desktop computer cells, scrap metal recovery, e-waste recycling, export for resale, refurbish and resell, individual reuse, that is also individual reuse, you see more price, you can put it on eBay and other places. So, this is the same values, put it in a pie chart where e-waste recycling, export for resale, refurbish. So, e-waste recycling was pretty high, then refurbish and resell is around 30%, even some people individual reuse, although price was much higher, but only 1%. So, some really good computers which was kind of out there. Laptop computer, again similar stuff, individual reuse is higher here, refurbish, resell, export for reuse. So, this is how for that particular university things got sold. So, in terms of profit associated with end of life pathways, if you individual reuse, this is the computer and the laptop, refurbish, resell, this price they got, export for resale, e-waste recycling, scrap metal. So, as you can say, of course, the individual reuse will fetch them the higher value, because somebody have found a computer which they think has a value, and then it must be much cheaper than what is available in the market. So, they went with this old computer which they can use it. And refurbish, resell and export for resell, even it goes abroad, e-waste recycling, scrap metal, of course, that will give you a lower value. So, when you are looking at any product, as we saw earlier, we have to put a due diligence to product fate. Now, as per the e-waste management rules, we have to do that. If you do not manage it properly, it becomes a liability to institution, data security, tag, revenue stream with low overhead. Large volume is actually managed much easily. So, we have to look at all these risks and benefits. What the other universities are doing, they are donating to local organization, sales through public auction, direct sales, contract e-waste recycling, OEM technology renewal program. So, there are different people are doing it differently. This is again it's a case study from a US perspective. In India, as per the e-waste management rules 2016, we have to manage it through the registered recyclers, registered collectors of electronic waste. There are donation programs, this is social benefit is there, extends lifespan, but dependent on age, low volume throughput, actually not much is in. Direct product resale, you can put it a deal and people can buy it. Revenue for institution requires time, labor, refurbishment, no knowledge of product fate, what will happen we do not know. So, and e-cycling, which is recycling is done, where some things output plastics, ferrous metal, shredding and all that, we talked about all that. Leasing can be leased out, and that is one way of doing it too. So, broader dimension of this challenge is we are in the US there is no federal policy. In India we do have a federal policy now. US they have the state level policy. So, it is not that US is behind us with us, but they have a state level policy, not a federal level policy. Patchwork state policy is there. There is still a lot of work needs to be done in US in terms of the electronics take back coalition. No science based best practices is out there. So, it is a product electronics lifestyle stages, we talked about that earlier. So, we need to have multiple best practices for institutional management. There are different things that could be done. So, that is kind of then we will quickly look at just in China and then we will stop. So, we started with e-waste in India and we e-waste in different places as well. Let us quickly look at what is happening in China and then we will close it. Just since China is similar to India and they also has a lot of issues similar to India. So, we will have a quick overview of China in next few minutes and then we will wrap up this video. So, the total amount of e-waste it is a sharp increase, as you can see, almost almost I think it is nearly 9 times, 8 to 9 times in 11 years. And now 16 to 80 kg per capita per year, much higher than India, is rising by 3% per year. And as you can see, an exponential increase and it is going up and up. The Chinese central government has banned import of e-waste now. So, it is they have a regulation in 2002, but it still e-waste does come in through Hong Kong and other places, but they are looking at actually banning not only e-waste, for any e-waste coming into China for recycling since last year, and things have been being followed very seriously now. So, actually they have illegally imported 57,000 tons of e-waste, which out of which 8,400 was exported again, but the remaining nearly 50,000 stayed in China. So, China's e-waste usually came from 3 major sources: household, institutional and schools, hospitals and all that, government equipment. There are 3 channels: second hand market, donate their to home appliance to poor people, obsolete e-waste to peddlers, and then peddlers sell such to e-waste dealers. So, they have a National Development and Reform Commission which was promoted circular economy in China. So, they are trying to promote e-waste recycling, encourage technological innovation. So, Tsinghua University developed a recycling technology in 2004, which is being used that they had only 8,000 home appliances. So, again they have a similar problem as what we have in India now, but they have this e-waste register like a e-waste recyclers, but the e-waste recyclers are not able to find they are not able to get enough material to recycle. So, they are not meeting the capacity. So, it is shut down, occasionally operated, same problem where we have. Another example is the UNEP, they come up with the electronic recycling pilot project. They paid marginal money and this as a result of informal sector, marginal money to collect those obsolete. Then there are 3 relevant rules: circular economy promotion rules, solid waste pollution control, clean production rules. So, those are used. The national reform this became in charge of resource efficiency. Then they had this Ministry of Environmental Impact came in, Ministry of Industry and Information Technology. Again, just give you some idea of how the rules in e-waste laws in China. I will not go over that in detail. So, there was how that China has made progression in terms of managing it in a much better way than what we are managing. So, it is there, and who is responsible for what in China as what we do it in India. So, you can compare. We kind of went over the Indian waste management rules quite in detail. So, I just provided you the Chinese rule just for those of you who are interested can compare that. Again, they have the similar issues here. Is implementation of this e-waste management rules, behavior of the informal sector, enforcement is not being effective, lack of effective collection system, technological challenges is there, lack of public participation, NGOs are not that much is coming out. So, that is how that, as you saw, it is very similar, but China has made some recent progress and in terms of the management of electronic waste. And if you look at how things are working in EU, here are a few slides to give you some information on that. No need to kind of read stuff from there. I will just show you some of these maps. So, as you can see, weight per capita, this is in the different European Union countries. we are seeing more and more small equipment. The small equipment is that peach color. As you can see, more and more peach colors have started dominating now small equipments. And then small IT equipment. Large equipment is your light blue color, which is another bigger category. So, as you can see, the smaller equipment is getting more popular as more and more cell phones and other things are coming out. And the small IT is that gray color. So, those are the gray and the peach. If you take that, that's nearly 1/3 to maybe slightly more than 1/3 in terms of, and this is weight per capita. Remember, weight of this small equipment is very less, and these are mostly PDAs, iPads, your mobile phones and all that. Again, some in terms of the different countries, weight per country, as you can see for Austria, Belgium. So, the country which you can identify the country which produces the most. So, this are, and of course, it depends on their population too. So, some of these data up to 2015 is the real data. From 2016 onwards is the like a it's a extra like a estimated data. It's a predicted data. So, from the different countries how the waste is being produced. Weight per collection category, as you can see, for the temperature exchange equipment is screen, lamps, large equipment, small equipment is the, and then small IT equipment. So, as you can see, for the different collection category, more and more e-waste is being collected for the different types of this large equipment is kind of going down and the small equipment is picking up. And this is some projection in terms of how things will project for 2019, 2020. 2018, as you can see, different categories. Again, this is small equipment is what I am trying to say. This small equipment, which is your cell phones, PDAs, iPads, mini laptops, those kind of stuff will start picking up in electronic waste stream. So, we can do urban mining, which is another concept. All these heavy metals and other things are there which should get taken out, can be done by urban mining. And they use different approaches for that. Those of you who are interested can read about it, and there are databases where the number of records are provided, where we have several records in terms of EU. So, that is just a quick look at that, and those of you who are taking exam, and many of you who are taking exam might be wondering, oh, he has covered so much material at the end. Those things are not for actually for the exam. Those EU or China, those were just for you to see. These courses are meant to excite you in this particular topic. It's a 4-week course. It's a pretty small course in term, and there is so much material that is out there. So, it's very difficult to cover each and every aspect in great detail. So, what we are trying to do here is just to show you some information, get you excited about this topic, and then you need to do self-learning on this particular topic. And any questions and discussions, feel free, like our discussion forum is there. You put it up there, and later on as well, if you have any interest to know more about this particular aspect, you can always send me email, but not right now. I cannot entertain several thousand emails, so sorry for that. But right now the mode of communication is discussion forum. After this after April of 2018, if some of you who are working on e-waste anywhere in the world and want to communicate on certain aspects, you are more than welcome. You can always find me on IIT Kharagpur website. So this is with this we close this particular session, particular course. In fact, from a theory point of view, there will be some tutorial video will be which we posted shortly. And so any question, any discussion, please put it on the discussion forum, and we'll be more than happy to answer. Again, thank you for taking this course. I hope you enjoyed it. And those of you who are going to take the exam, best of luck for your exam. And those of you who are not thinking of taking the exam, again, best of luck for whatever you want to use this information for. And if we can offer any help, please contact us presently through the discussion forum, and we'll be more than happy to answer your questions. Thank you.